Hello there, ladies and gentlemen. Welcome to another exciting edition of HL Chemistry Flip Classroom. This is Mr. Loafs, and let's get down to it, shall we? What we're going to talk about here is when we first did periodic table back in year one, there was some stuff that we skipped over, that mostly the HL stuff from that topic 13. So we're going to go back and hit some of that right now. Now, this particular material, what do I think of it? It's definitely not my favorite, especially certain aspects of it. I don't really understand why we need to know it or what's going on where this has to be part of what we're doing. But not my favorite, and some parts of this that I don't think you're going to be in love with either. But this goes along with a note sheet that is going to be made available to you probably in the workbook, but anyway, you don't have to write this all down. So basically we're going to talk about the oxides of period 3. So the elements that are found in period 3, sodium, magnesium, aluminum, silicon, etc., and combined with oxygen, the properties of those compounds. So for sodium there's only one, and when it comes to the formulas, these three especially, that should not be a problem. They're just the normal ionic compounds. Using the chart, we can predict those formulas. And then silicon can form SiO2. We've talked about silicon dioxide before. When we get to phosphorus, sulfur, and chlorine, there are a couple different options, or at least two that they want you to know of as far as oxides. So the oxidation number of the period 3 element, we should be able to do that from the redox unit, so that shouldn't be a problem. Electrical conductivity in the molten state. So again, if we think about what we've already learned and tie it into other things, ionic compounds do conduct electricity in the molten state. So sodium, magnesium, aluminum oxide are all ionic compounds, so they have high conductivity in the molten state. All of these are insoluble, so you can't really dissolve them, but like all ionic compounds, there are electrolytes. SiO2, remember, is a giant covalent structure, very little electrical conductivity, and then these, as we expect from covalent compounds, do not conduct electricity. And then again, the structure, we've talked about this before, ionic compounds, I don't know why it says giant ionic, to be honest, but giant covalent, and then molecular covalent. So again, this whole table should be normal stuff that we could just predict from the bonding unit and stuff that we've already talked about. Another thing we need to know about the oxides of period 3 is the acid-base behavior. The term amphoteric is substances that have the ability to act as an acid or a base. So as we move across the periodic table here, thinking about the acid-base character of these compounds, you kind of go from basic, the two compounds, or the farthest left compounds, are basic. Aluminum, which is kind of in the middle, is a amphoteric acid or a base, and then the other compounds are acidic in water. So we do need to know that, and we need to know this little pattern that we see here. We're going from basic to acidic. And then, I'm trying to throw a little word art, maybe putting a little twist on it to break this news to you, that all of these chemical reactions you're about to see on this whole slide need to be memorized. And, why, I don't know, but that is what IB has deemed necessary. So every single one of these equations that we're going to write down, you could potentially on a test, either in this class or in the real IB exam, be asked to reproduce them from memory. Reactants and products, the whole thing. So let's take a look at them. Like a question might ask you to use chemical equations to explain the acid-base behavior of the different oxides of period 3. So we see them reacting with water here. They both produce hydroxide. So there are a few patterns you can kind of use to help you. But both the sodium and the magnesium, which remember are the basic ones, they produce bases in solution. So hopefully you remember that hydroxide is associated with basicity, alkalinity. I don't know. But yeah, both of these are strong bases. So when we react these oxides with water, they produce strong bases. So therefore we consider them to be basic. When we put them in water, they form a basic solution. They also react with acids to produce a salt and a water. And so this is basically, if we think about neutralization reactions, we talked about in the acid-base unit, that's what it is. And remember the pattern there. is that we're going to get water and a salt when we do a neutralization reaction. So same thing here. My suggestion would be to try to remember some of these patterns rather than outright memorizing the whole reaction. Try to make some sense of it. But yeah, not a fan necessarily that we have to produce all these reactions. That's not my favorite thing, and J-Law doesn't like it either. Now, we talked about how the ones more towards the right are acidic, so when we mix them with water, we should expect to be seeing some acids produced. So we have the P4O10 and the P4O6 both reacting with water. One of them produces phosphoric acid, and one of them produces phosphorus acid. Something you'll see. So this is the acid-base naming system that we talked about. I don't know if I've mentioned this or not, but another way that these acids will be named is to say phosphoric, call them both phosphoric, but then put the oxidation state of the phosphorus in there. So in this compound, phosphorus has a +5 oxidation state, and in this compound it has a +3 oxidation state. So that's just another thing you might see in naming those, so I wanted to show that to you. But yes, we have to remember both of these reactions. Yeah, I don't know, it's just one of these things that we got to deal with. Mr. DeVito's not a fan, I'm not a fan either necessarily, but got to do it. So SO3 and SO2. Now these two reactions kind of serve double duty in that we also have to know them when we talk about acid rain. We may or may not have talked about that in class yet, so these kind of do double duty. But SO3, again, it's kind of similar to the last one. One of them produces sulfuric acid, one of them produces sulfurous acid. The one with more oxygens, produces the one with more oxygens on this side. So the SO2 turns into SO3. So yeah, just things we need to commit to memory, and not much I can tell you about that, or any hints I can give you. So then we have the two oxides of chlorine that it wants us to know. Again, they react with water to produce acids. We've got perchloric acid and hypochlorous acid, so two different acids produced there with the two chlorine oxides. So again, they're acidic in solution. So again, we've got to just deal with knowing those. All right, so SiO2, it doesn't really dissolve in water, so it doesn't react with water the ways that the other ones do, but it will react with a base. So whatever the base is, that's got hydroxides in it, hydroxide ions in it, it will react with that. So in that sense, it acts as a base. Again, aluminum oxide is not really soluble, so if you put it in water, it's not really going to do much, but it can react with both acids and bases. So here we see kind of a complex reaction where we have aluminum reacting with an acid or H+ ions to produce aluminum ions and water, and in this case, aluminum oxide and water and hydroxide ions making AlOH4, which is this weird kind of ion thing, which is going to be basically insoluble, I believe. So anyway, it's reacting with a base here, and it's sort of eliminating that base, kind of neutralizing it in a way. So that's why we consider that acidic, or rather that's why we consider it amphiphoteric, because it reacts with both acids and bases. Here we see the acid reaction, the base reaction, and again, yeah, we got to unfortunately be able to reproduce those reactions from memory. So that's the oxides of period 3, and that's where IB has deemed that we need to know about those. And then what we're going to talk about now is the general characteristics of the transition elements. And we've kind of talked about transition elements as the D block, that area in the center. It turns out the definition is slightly more complicated. A transition element is any element that forms at least one stable ion with a partially filled d orbital. So for example, that's the electron configuration of Cu. The concentration of Cu, rather the electron configuration of Cu+2 is that. So Cu meets the definition of an transition element because it does form this Cu+2 ion that has a partially filled d orbital. A full d orbital would be 310. So the Cu+2 ion has a partially filled d orbital, and that's the definition of a transition element. Zinc, actually, despite being in that D block, is technically not considered a transition element because it only forms one type of ion, which is Zn2+, and the Zn2+ ion does not have a partially filled d orbital. It has a full d orbital. 10 is the maximum that d holds. So here's the zinc electron configuration, zinc +2. It has no partially filled d orbitals, so it is not technically considered a transition element. This is just some of the electron configurations of some of the different elements. One thing that we notice is a lot of them have unpaired d electrons, at least one, in their d orbitals there. So we're going to be talking about some characteristics of transition elements, and we need to be able to attempt to explain why that's the case. So as we go left to right, this is stuff we've talked about in the periodic table in the beginning. Last year we talked about the periodic table. Effective nuclear charge is the charge the electrons feel from the nucleus. And as we go to the right, we add protons. It creates a greater effective nuclear charge across the periodic table when we go to the right. But with the transition elements, if you remember, the electrons go from like 4s to 3d or 5s to 4d as you write out the electron configuration. So it somewhat negates the effect. It definitely makes it a little bit different, or the pattern is a little bit different in the transition elements. And I'll show you some examples of what I'm talking about here. The 4s and 3d electrons or 5s and 4d or whatever are pretty similar in energy. They're more similar in energy than normal, I guess, when you're talking about electrons in two different energy levels. So that's another kind of thing. But basically, transition elements are more similar than main group elements when observing various periodic trends. So for example, here we have radius versus, these are main group elements, not transition elements. And then here are, well, some main group elements, but transition elements here in the middle. And, the graph is flatter. There's not as much change as we move to the right in radius, so they're more similar to each other. Here's the ionization energy, first ionization energy as we go to the right. Here's some of our main group elements. So a pretty big change. But then, again, within our transition elements here, which would be like these, there's definitely a lesser amount of change. They definitely still change, but there's a lesser amount of change as we move between elements. So their first ionization energies are more similar. So here's some properties of transition elements. Most of the metals that we actually use as metals are all in that transition element section, in terms of metallic objects and things that you think about in terms of metals. When I say use them, they tend to be better conductors of heat and electricity. They're more malleable. You can bend them better. You can make wire out of them better. They're ductile, high tensile strength, hold loads without breaking. So the transition elements are superior in that sense. And transition metals all form more than one stable ion. Main group elements, metals, form only one ion, so sodium Na+. There's no other options here. And this is successive ionization energy. So remember what that is taking more than one electron from the same atom. So we take one electron away, and it's +1, another electron is +2. So here we have a main group element, calcium, compared to transition element, vanadium. And you can see that there's definitely a kind of a faster and a greater increase in ionization energies in calcium as compared to vanadium. So the successive ionization energies are more similar. I guess it's just not as steep of an increase in successive ionization energies. So basically what that means is it gives us more options. Vanadium can have several oxidation states. It doesn't take quite as much energy to take that next electron away. So it allows for there to be more ionization states in the different transition elements. So what you see here, this is a table of possible oxidation states for different transition elements in period 4. Manganese has the most, +7, +6, +4, +3, +2. So lots of options there. And then, so generally the oxidation number, the maximum oxidation number increases to manganese, and then it kind of decreases. Now, these ones, like scandium does sometimes form. I know I said transition elements always form more than one stable ion, so scandium definitely does, as does nickel and copper. So they're kind of showing some of the more common oxidation states here. Zinc is the only one that truly only forms +2 ions, but it's not a transition element. There's a table of oxidation states actually in your data booklet. So every transition element, at least in some cases, can form +2 and +3 ions, mainly because of that. They all have those 2s electrons, like 4s, 3d, 5s2, 4D, where it can lose those two and form +2. And as we've talked about, you always remove the S subshell electrons before you remove the D subshell electrons. Basically, in the first half, from scandium to chromium, +3 state is going to be more stable and more common. And then when you go from the second half, manganese to zinc, the +2 oxidation state is one of the more stable and more common ones. Transition elements with high oxidation states often make good oxidizing agents because then they can get reduced. You know, if you got an oxidation state of +7, like chromium does here, I believe, you know, that gives you a lot of room, sort of, if you want to think of it that way, to take electrons and lower your oxidation number. And therefore, since you're getting reduced, you're a good oxidizing agent. And as I mentioned, yeah, there's a table of common oxidation states. If you're ever asked about it or curious about it, there are some in there. Another characteristic of transition elements is they form complex ions that have a color, and we're going to spend a whole lesson talking about that, so we're going to talk about that more later, but I'll just bring it up now when we're talking about properties of transition states. So here's vanadium in 4 different oxidation states, and it has actually different colors in each oxidation state, and we're going to talk about why that's the case. Another property of transition elements is they're often important catalysts, and they can form weak bonds with S and D electrons, which allows them to catalyze some things. I think we've used the terms heterogeneous and homogeneous catalysts before, but just to remind you, heterogeneous catalysts are in a different phase than the things it's catalyzing. So most common example probably would be a solid catalyzing a gas reaction, like solid iron is used in what's called the Haber process to make ammonia, or your catalytic converter in your car converts some of the gases in your exhaust and helps out with pollution and other things like that. But it's a metal that's catalyzing a gas reaction. Homogeneous catalysts are in the same phase. Fe+2 ions help hemoglobin carry oxygen. And various other transition elements will do some catalyzing if they're in solution and catalyzing a reaction that's also in solution. So heterogeneous catalyst is in a different phase, homogeneous in the same phase, and transition elements tend to be good catalysts. You know, I'm getting so old that even some references to things that happened way after I started teaching are getting old. I don't know if you know these guys. This was, I think, in about 2010. This is the Insane Clown Posse. They came out with a song called Miracles, and it's, you know, in my opinion, kind of a silly song. And one line that is in there that people made a lot of fun of was they were wondering how magnets work. They used a swear word in there, which I won't repeat, but and people made fun of them for asking how magnets work, but the fact is, almost no one really knows. Your everyday person does not know how a magnet works, and it's actually kind of complicated. But one thing that comes along with being a transition element or another property is magnetism. Now, there's 3 types of magnetism we're going to talk about. Diamagnetism is basically what all substances have. It's a force that repels the magnetic field, a magnetic field. It's not something that you would really notice in everyday life at all. It's very weak, but it's caused by paired electrons. So just about everything has paired electrons. You know, when we think of an orbital, most of the time in most types of things, those elements are paired up. Paramagnetism is caused by things with unpaired electrons. It produces an attraction to magnetic field. It's stronger than diamagnetism, but still not really what you think of when you think of a magnet. And so any transition metal at all that's got some unpaired electrons can show paramagnetism. And that is one thing that transition elements tend to have is unpaired electrons in those d orbitals. So that's paramagnetism. And then the last type of magnetism, which is, again, when you think about magnetism, this is what you're thinking of, which is ferromagnetism. So things we observe being attracted to a magnet, as well as magnets themselves, are ferromagnetic. It's actually only cobalt, iron, and nickel that are ferromagnetic. And the thing about them is they have large numbers of unpaired electrons. So basically, an electron itself is kind of like a little top with a magnetic field, and generally speaking, these electric fields of the electrons are all sort of oriented in different ways and kind of like cancel each other out. But what can happen with these particular elements that are ferromagnetic is we can get those unpaired d electrons kind of oriented in the same direction, and they can therefore be much more attracted to a magnet than other things, actually stick to magnets and whatnot. And the big thing that makes ferromagnetism different than paramagnetic is these types of objects will retain some degree of magnetism even if you remove the magnet from them or take them away. Like, I don't know if you ever noticed, but sometimes you're playing around with a strong magnet with something that's attracted to the magnet, like a paper clip maybe, and then you remove the magnet. That paper clip itself can then exhibit some magnetism and like pick up another magnet. And this is the basis of like hard drives and a lot of those things. There's kind of almost a memory to the magnets that they've been exposed to. So, so the hard drive technology and certain things utilize that. So this is just an example of two different objects, a paramagnetic object and a ferromagnetic object. And so, like I said, in the no magnetic field, the electrons are kind of oriented different ways. All their little magnetic fields kind of cancel out. But if we are in a magnetic field, they kind of line up together and get all facing the same direction. And if something's ferromagnetic, we really have a bunch of different electrons kind of working together, organized in the same fashion, pointing the same direction. Whereas in paramagnetism, they're kind of organized, but not really all pointing the same way. So that's kind of it in a nutshell. So one thing that would be nice to do, great for your learning, is right at this moment summarize these own notes, make a little list of the key characteristics of transition elements, kind of reflect on what you've just seen, and make a little list there. But that is it, ladies and gentlemen. I'm all finished. Thank you very much for watching. I hope you're having a great day, night, whatever. I hope it's not too late at night. If it is, go to bed, kids. Get some rest. Thanks, and we'll see you soon. Bye.